Evolution, defined by Charles Darwin as the process by which species develop through natural selection, with small mutations and adaptations at an individual level that lead to large-scale development at the population level. This is where species evolve to increase their chance of survival in their environments. Evolution begins at the individual level, and this can be easily seen in bird populations. Groups separated by geographical barriers are forced to adapt. As some individuals die, others more suited to the environment survive and pass on the genetic information to their offspring. Eventually, they have a chance at becoming a distinct species adapted to a very specific set of living conditions. In modern water birds, for example, terns have evolved to be able to dive into water for food, while sanderlings have evolved to fill a different niche along the shoreline, and still other birds, such as the turnstone, live further inland. Speciation through natural selection has allowed for the development of more efficient ecosystems, where many unique species can survive by filling different niches and using different resources. Though these species vary at a population level, they were only able to arrive at that point through individual differences. These can arise through simple random genetic mutation or variance due to reproduction. Though speciation is visible today, to understand the process of evolution we have to look back in time for thousands, millions, and even billions of years. The major periods of life are divided into three main sections: the Paleozoic, Mesozoic, and Cenozoic time periods. Throughout all three, there have been several mass extinctions, which have paved the way for a mass evolution of extremely different species. After the mass extinction between Triassic and Jurassic times, a genus of dinosaurs known as theropods emerged. We can see the evolution of birds from theropods through the development, gain, and loss of specific physical features, such as how all birds have hip bones with openings in the sockets, which is a key characteristic of theropods, the only main difference being that now the forelimbs of birds are longer than their hind limbs, which allows for easier flight and wing adaptations. Archaeopteryx, on the left, is one of the earliest known birds. 30 million years after Archaeopteryx existed, however, more modern-looking birds had begun to appear, like the Cynomys that gained features like a deep breastbone and smaller tail, but still retained many characteristics of Archaeopteryx. Beyond the socketed hip bones, modern birds also retained a significant amount of other theropod features. Highlighted here is the wishbone on both a theropod and the modern falcon. There is also the crescent-shaped wrist bone, the key open hip sockets, and the extended pubis bone. The fact that these shared features remained throughout time, while others changed through adaptation, provides historical evidence for evolution, which is simply a population-level change over time. After the initial appearance of birds with more modern features, another mass extinction gave rise to a more diverse array of species, beyond even just birds. This was a time when speciation of birds, however, was extremely abundant, and specialized birds began to take on even more explicitly modern features, indicating less of a need for large population-level change, and also demonstrating the incredible amount of time it takes for visible speciation to occur. The features of a seabird from the Eocene era, for example, which is on the left, and is dated to be between 56 and 34 million years old, are still carried in the modern fulmaris, or Arctic fulmar, with one key difference being the loss of several struts in the beak. The kingfisher, also from the Eocene era and shown on the left, has a similar bone structure to a modern belted kingfisher. Rather than simply continue to point out the maintenance of old characteristics in new species, let's take a look at a visual representation of these changes. A phylogenetic tree, such as this one, is like a roadmap, branching off where certain key features of a common ancestor were lost or replaced by adaptations, more useful in a specific environment. While at some point all life was ocean-based, a phylogenetic tree makes it simple to see how life developed and evolved from that starting point to create the species that we know today. And now, today, in the Quaternary period of the Cenozoic era, we are experiencing a sixth mass extinction. While previous occurrences have left the world ripe with abundant resources and easily partitioned for evolving species, we have no way of knowing what birds will effectively adapt to current global conditions and evolve to become new species. With current genetic technology, it is possible to identify evolutionary branches on a more complex level than simply phenotypic features identified through fossil analysis. But we still cannot predict the future of the world.